In this slide, we have an example to use the modified Newton-Raphson for multiple roots. We will actually compare the regular Newton-Raphson and modified Newton-Raphson here. On the left-hand side, these results are obtained by using the regular Newton-Raphson. On the right-hand side, these results were obtained using the modified Newton-Raphson. And let's show how we obtain them now. For the regular Newton-Raphson, let's write it here. Regular Newton-Raphson. If you remember, our formulation was xi plus 1 is equivalent to xi minus f xi divided by f prime xi. This is the regular one. So what we need is, we have function value, it's here, and also the derivative. Then let's use the derivative over here. By the way, let's say this is f prime x, and the derivative actually, let's write here derivative 3x squared minus 10x plus 7. So also, if you remember this function, if we separate these into some multiplications, actually that is fx equivalent to x minus 3, x minus 1, and x minus 1. So we have multiple root here. We can easily find the roots here, but we are just making this as a practice by assuming that we don't know the roots, and we use the Newton-Raphson. So we got the derivative as well. Let's use them in the formulation here and this one here. If we write them, our Newton-Raphson formula for this example becomes like minus xi minus x cubed minus 5x squared plus 7x minus 3 divided by the derivative, which x squared 3x squared minus 10x plus 7. And now we can start from I equals 0. Then for the initial guess is 0, x0 is 0. If we use this in here, I is, so x, we find x1 now, then equals x0 minus, and x0 is 0 actually, 0 minus, here 0 cube minus 5 times 0 squared time plus 7 times 0 minus 3 divided by 3 times 0 square minus 10 times 0 plus 7 equivalent to, this x1 becomes, at the top we have minus 3, at the bottom we have 7 only, so it's 3 divided by 7 like this, and it becomes 0.4285714. It's here already in the first iteration, this one. You can calculate the true value as well, because we know the true value of this in the previous slides. Actually, the true value is, we know that it's 1 over here. So based on 1, we can calculate that. Now I equals 1. Let's use that. x1 is equivalent to this value, 0.4285714. If we use this, x2 in the Newton-Raphson method becomes, I will not write the details, you can calculate them, 14.3, and you can see that we can continue on this. When we continue, we have these values, and eventually it goes to 1. Actually, the true value is 1. It goes to 1, approaches to 1, but very slowly. You can see we need to continue over here to have a very low error. This is still 2% over here. We need to go further, maybe 10 iterations. It takes time. But when we use the regular, not the regular, the modified Newton-Raphson, let's use it here. Modified Newton-Raphson. In that case, if you remember, we were using the ux equals f divided by f prime in the formulation, and from that we were having this formulation for this, xi plus 1 is equivalent to xi minus f xi f prime xi divided by f prime xi square minus f xi f double prime xi. Now we have the second derivative. We need the second derivative as well. That's why let me write here the second derivative too, and it is 6x minus 10. If we write them all, we will have the xi value as, let me quickly erase this and use this gap for our modified Newton-Raphson. So xi plus 1 is equivalent to xi, and in here minus fxi is x cubed minus 5x squared plus 7x minus 3, and the derivative is 3x squared minus 10x plus 7, and divided by f prime square, that means 3x squared minus 10x plus 7 and its square minus fxi, x cubed minus 5x squared plus 7x minus 3, and we will multiply this by the second derivative, which is 6x minus 10. And these x's are i's actually, xi. So let's write them down too. Here as well, on the left side, we have I values here. So then let's start with I equals 0. Then x1 is, when you put, let's say first xi, that means x0 is 0 actually from the beginning here. And when we substitute this into the equation, x1 becomes 1.10526. You can make the calculations, I will not. And the error becomes this actually, with this value. Then I equals 1. x1 is this 1.10526. Then we will calculate x2 here, and it becomes 1.003082. And for I equals 2, x2 is 1.003082. When we use modified Newton-Raphson method, x3 is very close to 1. It's almost 1. So it's very small error in 3 iterations, you can see. So on the right hand side, even after 6 iterations, we have an error of 2.2. But on the right hand side, you can see that at iteration 3, we have a very small error, which shows the effectiveness of the modified Newton-Raphson for multiple roots. If we try to approach to multiple roots, this is very useful, the modified Raphson. But what if we want to approach to the single root over here? Then the regular Newton-Raphson can still be efficient. Let's show that in the next slide. And in this slide, we continue to example 610, and we want to approach to the single root, which is x equals 3. In the previous slide, we tried to approach to multiple root, x equals 1, and we gave an initial guess closer to that one. And if we give a closer initial guess to a root, then it will converge to that root, which was the multiple root in the previous slide. But in this slide, to be able to approach to 3, we need to give an initial guess closer to 3. It can be 4, maybe it can be 2. It should be closer to 3, otherwise you can go to 1 instead of going to 3. And when we have 4 as the initial guess, the standard Newton-Raphson method, you can see that even after third iteration or fourth iteration, we have good error values and we approached quickly. But in this scenario, the modified one is going a little bit slower. You can see it still goes to 3, but slower than the standard one. So these results are showing that if we are going to a multiple root, modified is faster. If we are going for a single root, the standard seems to be faster. That's why we can say standard method is somewhat more efficient if we are going to the single root. And this example shows the trade-offs involved in opting for the modified Newton-Raphson method for determining a route. Although it is preferable for multiple routes, it is somewhat less efficient and requires more computational effort than the standard method for simple routes. So if you know that you have simple means single routes actually. If you know that there is single routes, then go with this standard. But if you know that there are multiple routes or there is a chance of having multiple routes, then go with the modified.